Hydrogen has always been the world's most abundant element, yet ironically one of its hardest fuels to make cleanly and affordably. For decades, scientists and engineers have been chasing a simple but stubborn goal: producing green hydrogen cheaply enough to compete with fossil fuels. That magic number, the benchmark whispered in conference halls and investor pitches around the world, is $2 per kilogram. Hitting that price point doesn't just make green hydrogen viable, it makes it transformational. It's the threshold where hydrogen can start replacing natural gas, powering industries, fueling transportation, and enabling a true zero-carbon economy. But to get there, the hydrogen industry has had to confront a paradox. To make a clean fuel, it's been consuming one of our most valuable resources: clean water. Producing a single kilogram of hydrogen requires about 9 liters of purified water. At small scale, that doesn't sound like much. But at the scale of gigawatt-class hydrogen plants, we're talking millions of liters every day. Water that must be filtered, deionized, and treated to near laboratory purity before it can enter the electrolyzer. This is because most electrolyzers, especially those based on PM or alkaline technology, are extremely sensitive to impurities. Even small traces of minerals, chlorides, or organics can corrode catalysts or clog membranes. Now imagine building a massive hydrogen project in an arid region, somewhere like the Middle East, Chile's Atacama Desert, or Northern Africa, where sunlight and wind are abundant, but fresh water is scarce. It's a contradiction that has been quietly haunting the industry. We're trying to solve one sustainability problem by potentially creating another. But what if hydrogen production didn't have to rely on clean water? What if it could use something we already throw away: wastewater? That's the breakthrough idea behind a new study by scientists in the United States, who have shown that reclaimed wastewater can be used in electrolyzers to produce hydrogen fuel without the need for ultra-pure water. And this one innovation might be enough to nudge the hydrogen industry closer to that 2 kWh goal. Let's unpack how this works and why it matters. In traditional electrolysis, you start with water molecules, 2 parts hydrogen, 1 part oxygen, and pass an electrical current through them using renewable power, usually solar or wind. The electricity splits the bonds, releasing hydrogen gas at the cathode and oxygen at the anode. The concept is simple, the challenge is in the details. Every impurity in that water can interfere with the reaction, reduce efficiency, or damage the system. That's why commercial plants go to great lengths to feed only the purest possible water into the electrolyzers. They use multi-stage purification processes: reverse osmosis, ion exchange, electrodeionization, all of which consume energy and money. The Princeton research team approached the problem from a different angle. Instead of trying to make dirty water clean enough for the electrolyzer, they asked, can we make the electrolyzer tough enough for dirty water? They developed a specialized coating for the electrodes that resists fouling from organic compounds and salts. Typically found in wastewater, the coating prevents contaminants from sticking to the catalyst surface, allowing the electrochemical reaction to proceed efficiently even with non-pure water. The results were surprising. In controlled tests, electrolyzers using treated wastewater produced hydrogen at nearly the same rate and efficiency as systems using ultra-pure water. There was a slight reduction in performance, but it was small enough to be offset by the massive savings in water treatment and sourcing costs. This is more than a laboratory curiosity, and it's a potential game changer for hydrogen economics. In the grand equation of levelized cost of hydrogen, LCOH, electricity accounts for the lion's share, typically 60 to 70% of total costs. But the remaining portion, which includes water, purification, maintenance, and logistics, still matters. By removing the need for ultra-pure water, you can reduce both capital and operational expenses. More importantly, you eliminate a key barrier for siting hydrogen projects in regions with limited freshwater access. Let's imagine a real scenario. Suppose you're a developer planning a 200-megawatt hydrogen plant near a coastal industrial zone. You have access to cheap solar power, abundant wind, and existing industrial infrastructure. But water is a sticking point. Desalination adds extra cost And transporting clean water inland is expensive and politically sensitive. If your electrolyzers could run on treated municipal wastewater, the entire equation changes. You could partner with a local wastewater treatment facility, use its effluent as feedstock, and even provide oxygen from your process to improve its aeration system. That's circular economy design in action. Two industries helping each other achieve sustainability. Beyond cost savings, the environmental optics are strong. Critics of hydrogen often point out its water demand, particularly in countries already facing drought. Using wastewater neutralizes that argument. Instead of competing with agriculture or human consumption, hydrogen production becomes part of a water recycling solution. It transforms a waste product into a valuable input for clean fuel, turning an environmental liability into an economic asset. The implications ripple outward. Urban regions could develop small to medium hydrogen hubs co-located with water treatment plants, turning cities into distributed producers of green fuel. Industrial parks could recycle processed water for hydrogen production instead of discharging it. Even remote communities could integrate wastewater treatment with localized hydrogen generation, providing both sanitation and clean energy. This innovation also opens new avenues for policy and financing. Many hydrogen projects today struggle with permitting around water use and environmental impact assessments. Demonstrating that a project uses reclaimed wastewater instead of potable water could make it easier to secure environmental approvals, community support, and even green financing. Institutions like the World Bank and Green Climate Fund are increasingly prioritizing circular resource use, and wastewater-based hydrogen projects fit that framework perfectly. Technically, challenges remain. Wastewater isn't uniform. Its composition varies by source, treatment level, and season. It contains salts, ammonia, organic matter, and heavy metals that can still degrade electrolyzer components over time. The Princeton team's solution addresses part of the problem, but scaling it will require robust pre-filtration systems, periodic maintenance, and perhaps modular electrolyzers designed specifically for variable water quality. Fortunately, these are engineering problems, not scientific impossibilities. As electrolyzer technology matures, it's likely to become more tolerant and adaptable. For developers and consultants, this is where innovation meets opportunity. The ability to pair hydrogen projects with wastewater infrastructure creates a new category of investment: water-energy symbiosis projects. These projects appeal to municipalities looking to modernize aging treatment facilities while reducing their carbon footprint. Imagine a city upgrading its wastewater plant with solar panels, electrolyzers, and storage tanks, producing green hydrogen for municipal buses, sanitation fleets, or local industry. It's not just clean energy, it's clean infrastructure. From a financial standpoint, that synergy can unlock multiple revenue streams. Wastewater plants typically incur costs to dispose of sludge and excess water. By diverting part of that stream into hydrogen production, they can generate new income. Meanwhile, the hydrogen plant benefits from a low-cost, stable water source. It's a classic win-win model. Now, let's zoom back out to the global hydrogen picture. Why is everyone chasing $2? Because that's the cost level where green hydrogen becomes competitive with gray hydrogen, the kind made from natural gas without carbon capture. At that price, industries like ammonia production, methanol synthesis, and steelmaking can switch to green hydrogen without massive cost penalties. It's the tipping point for market adoption. Reaching that threshold requires a holistic attack on costs, lowering electricity prices, improving electrolyzer efficiency, streamlining permitting, and yes, reducing water expenses. Wastewater electrolysis directly contributes to that last piece while also strengthening the sustainability story. If you're presenting a hydrogen project to financiers, imagine how much stronger your case becomes when you can say, "We're not consuming clean water, we're recycling waste." That's the kind of language that resonates with ESG-focused investors and policymakers. Let's not forget the regional implications. In arid regions like North Africa, the Arabian Peninsula, or Western Australia, water scarcity is one of the biggest hurdles to large-scale hydrogen production. Desalination is an option but adds complexity and energy cost. Wastewater, on the other hand, is already available in abundance near population centers. Using it not only reduces cost, but also helps cities achieve their waste management goals. That alignment between industrial strategy and municipal sustainability could accelerate hydrogen adoption far faster than technical improvements alone. There's also a global justice aspect to consider. One critique of the green hydrogen boom is that it risks reproducing the same resource inequalities that plagued fossil fuels, exporting energy from resource-rich but water-poor nations to wealthy markets. By integrating wastewater use, hydrogen can become more equitable. It enables developing nations to produce clean energy without depleting scarce freshwater supplies. The science itself is elegant in its simplicity. Electrolysis doesn't care where the water comes from, as long as it's conductive and stable. By developing protective catalysts and robust membranes, researchers are essentially teaching electrolyzers to tolerate the real world, to operate not just in pristine lab conditions, but in the messy, unpredictable environments where energy is actually needed. That's how revolutions happen, not by perfecting the ideal, but by adapting to the imperfect. Let's think about scale. A city of 1 million people typically produces about 100 million gallons of wastewater daily. Even if a small fraction of that, say 10%, were diverted to hydrogen production, it could yield several tons of hydrogen every day. That's enough to fuel a fleet of public buses, supply backup power systems, or feed local industries. Multiply that by thousands of cities worldwide, and you start to see the potential magnitude of this innovation. The 2 Sattler Keyless goal may still be years away, but every efficiency gain, every cost reduction, every smart integration like this moves us closer. Wastewater electrolysis may not single-handedly redefine hydrogen economics, but it contributes to the cumulative progress that eventually makes clean hydrogen mainstream. It's one more step in transforming hydrogen from a niche technology into a cornerstone of the global energy transition. For developers watching this, the lesson is clear. Think beyond the electrolyzer. Think about the entire system. Water sourcing, waste management, and industrial integration all influence the bottom line. A smart hydrogen project isn't just efficient, it's synergistic. It aligns with existing infrastructure, local resources, and community needs. As the hydrogen market matures, we'll see more of these hybrid configurations. Hydrogen plants connected to desalination units, fertilizer factories, or wastewater treatment facilities. Each integration will shave costs, share resources, and create new pathways to profitability. The future of hydrogen won't be built by chasing efficiency alone. It will be built by connecting dots that others overlook. Of course, wastewater electrolysis also raises interesting regulatory questions. How do we classify hydrogen made from wastewater? Is it still considered green hydrogen under certification schemes like the EU's Renewable Energy Directive or the US Inflation Reduction Act? These policies often tie incentives to renewable power input, but they may soon need to account for water source sustainability as well. That's an emerging policy frontier, and another reason why early adopters of this technology could shape future standards. Ultimately, the story of hydrogen has always been about turning challenges into opportunities. We started with a molecule that's abundant but elusive, powerful but difficult to handle. And now we're learning that its production can become cleaner, not by using more resources, but by reusing what we already have. The idea of producing hydrogen from wastewater captures the spirit of innovation that defines the clean energy movement, transforming yesterday's waste into tomorrow's energy. So, could this wastewater experiment truly unlock tu kagahadus green hydrogen? The short answer is not alone, but it could make the journey a lot faster and a lot smarter. By lowering costs, expanding site options, and improving sustainability, it strengthens every link in the hydrogen value chain. It's an example of how interdisciplinary research, chemistry, engineering, environmental science can converge to solve one of the toughest problems in the energy transition. Hydrogen's next frontier might not be found in futuristic reactors or exotic catalysts, but in the humble streams of water that flow beneath our cities every day. Wastewater, once a symbol of pollution and decay, could become a cornerstone of the clean energy future. If you're a developer, consultant, or investor, exploring how to integrate such innovations into real hydrogen projects, from feasibility to finance. Check out h2hub.greenyenergy.com. You'll find practical tools, project templates, and AI-powered simulators designed to help you evaluate site conditions, estimate levelized cost of hydrogen, and design financially sound projects that meet both technical and environmental goals. Because the future of green hydrogen won't just be about electrons, it will be about ecosystems. And as this wastewater experiment shows, sometimes the most powerful solutions don't come from finding new resources. They come from reimagining the ones we already have.